subtracting them?
Multiplying.
Multiplying, exactly. So what this is saying is to go from the short side to the long side, you're going to multiply by root 2, right? So to go this direction, what would you do?
Divided by 2.
Divide it by root 2, not 2. So let's say that I was giving you, here's the same triangle. It's still 45, 45, 90, right?
Mm-hmm.
And this is 3 root 2. What's that side going to be?
You should be divided by root 2 on this way, so you put times by root 2.
Mm-hmm.
So if you do that times root 2, you get that.
So, where did the 6 come from?
I think there's 3 times 2, you have to do that.
But you don't have a 2 there. You have a root 2 and a root 2. So there was never a 2 in the first place.
Oh, when you do root 2 times root 2, you get 2.
Exactly. So
I forgot about
it's going to be 3 times root 2 times root 2, which is 3 times 2, which is 6. There you go. Good. So if you had 6 here, right, let's say that you have a triangle, and you get 8 for this side.
Yeah.
What's this side going to be? If it's a 45, 45, 90.
It would be 4 root 2.
Well, you divide by root 2. So
Oh, it would be just 4.
8 over the square root of 2. Did you guys learn about rationalization yet?
We learned about it, but it's been a while.
Okay.
We're on
So
different
you're
topics.
not allowed to have a radical on the bottom, right?
So you have to do the fraction.
We have to do the fraction of root 2 over root 2 to cancel it out. 8 root 2 is just 8 root 2, right? And then root 2 times root 2 is
2, and then you cross out that,
and
right?
you get
And 4.
4 root 2.
4 root 2.
So this is 4 root 2, 4 root 2, 8, 3 root 2, 3 root 2, 6, 7, 7, 7 root 2, 5 root 2, 5, 5. In other words, it's always a consistent relationship that you can use no matter what you're trying to figure out. But the simple rule is that when you're going from the short side to the long side, you times root 2. When you're going from the long side to the short side, you divide by root 2. Good?
Yeah.
And then, did you also do the 30, 60, 90s?
Yes.
Okay. What's the ratio there?
30, 69, doesn't that have something to do with dividing by 3, or divided by root 3?
Well, it's just root 3. The way I remember it is that if there's 2 different sides, it's root 2. If there's 3 different sides, it's root 3. And so let's say that this is 1, right, on the short side.
Right.
What's the long side going to be?
1 root 3?
Nope, 2.
What would be 2?
Because that's the ratio. It always is. The long side to the short side is double.
Oh.
And the short side to the medium side is what?
Not sure.
Root 3. This is the root 3.
Oh, so that's what I was just talking about.
So if this was 6, this would be
3.
and this would be
3 root 3?
3 root 3. If this was 5, this would be
10.
and this would be
10 root 3?
5 root 3. It's got to go from the short side to the medium side.
Oh.
So you have to go, basically you have to go this way. If you're given this one, go to this one, then this one. And if you're given this one, go to this one, then that one. So 6, 3, 3 root 3, 8, 4, 4 root 3, 12, 6, 6 root 3, 20, 10, 10 root 3. Always the same relation. Cut it in half, multiply by root 3. Divide by root 3, double it. And so you can go back and forth. So really you're going to see these two like really frequently. Now the reason that you like learn about these two largely is because they're half of other shapes. A 40 from 45, 90 is half of a square. So it's not just the hypotenuse of the 45, 45, 90, it's also the diagonal of a square. And this, if you take a 30, 60, 90 and put it on the other side of a 30, 60, 90, what do you get?
Another triangle.
An equilateral triangle. 60, 60, 60.
Right.
So you get 2 and then
So
this is half.
there's been one time where they did that thing where you have to find
The height, because you want to
The
find
height.
the
altitude.
altitude. And what's that used for?
The proportion, just on another paper.
Area.
Ah,
Because
okay.
you use the height and the base to figure out the area of a triangle.
Right.
Make sense? Okay. Any luck?
No, where would the stuff be? Why is it not in there? I told you to bring it all. It's not in there. And this is like part of the problem, because all the papers are in here like completely unorganized, so we'll have to work on the organization of it. She doesn't have it.
Okay.
So,
Were there any other special right triangles in number 2? Was it just those?
Just those two.
Okay.
Those are the only two, yeah.
Are there any questions that you remember not knowing how to do with those other than the ones we just talked about?
No, I don't think so. What about radicals? Just doing radicals by itself.
Just simplifying radicals,
Yeah.
multiplying radicals. So,
Okay.
I think it was just a simplifying though.
Now there's different
simplifying.
levels of doing that. So have you guys talked about the absolute value stuff, like the little lines around things?
They didn't
No.
do that, so
So you guys haven't done that stuff yet? All right.
So she just needs simplifying radicals.
Have you been doing it just with numbers or with variables as well? Like have you done stuff like the square root of 48 to the third?
No.
Nothing like this? Okay. Was it just variables, just numbers, both?
It was like just numbers.
Just numbers? Okay. So like you're asked things like what's the square root of 81? What's the square root of 90?
Yeah, like some were perfect squares and others weren't perfect squares and you couldn't put a decimal.
Okay. So what would you do for this one, given that it wasn't a perfect square?
9, 10, and 3.
It's not just 3 though, it's 3 and 3. There you go.
So, then you have to times something. I forget what you're supposed to be multiplying.
You don't have to multiply anything. What you need to look for is perfect pairs. Because what you're looking for is square roots, numbers that multiply by themselves to get that original number. So do you have any pairs in that set of numbers that you factored out? 3. So you can pull out a 3, and what do you have left?
Oh, when you times with 3, don't you just get 3?
Well, exactly. So in other words, you're taking out the pair of 3s and putting that outside the radical. It's been square rooted down to 3,
Okay.
right? And then is there anything else under the radical that's in pairs?
No.
So now you put it back together, you recompose the number, and you get 3 root
Radical.
10. Exactly. So root 90 is 3 root 10. They're exactly the same.
Okay.
Good?
Yeah.
Do you remember problems that you were having with these that were really hard that you weren't sure what to do with?
It was like a triangle, and then they would give you a number, and then you would have to find the radical. Like, in the triangle, they would probably give you something like that, and then you would have to find the radical based on, like 45, 45, 90, or something like that.
Now when you say find the radical, you've already got the radicals, right? You can't simplify root 6 anymore. So what were they, when you said find the radical, what were they looking for?
Probably the other number, but
So like, let me, alright, so you're saying something like this is 6 root 6 and this is 4 root 3, and there's a right angle here. What's this length?
yes.
Okay, so what would you do with that?
Well, you can't really square that because
Sure you can. You can square anything.
You can?
Now be careful there. What operation is between the 4 and the root 3?
Don't you have to rationalize that?
Well, there's no rationalization, because rationalization only deals with fractions. When you're just looking at 4 root 3, what connects the 4 to the root 3? Are you adding them, subtracting them?
Times.
You're multiplying them, right? And then you're raising this to the power of 2,
Right.
right? Do you guys go over PEMDAS in your class?
Yes.
Okay. So the order says parentheses.
Exponents, multiplication.
Exactly. So you have an exponent here and you have a multiplication. Which one comes first?
I think it's exponents.
The exponents happen before you multiply, right? But what are you squaring here? Are you squaring the root 3 or are you squaring 4 root 3?
4 root 3.
So if you want to square 4 and the root 3, you need to have parentheses there so that you're squaring both numbers. Otherwise, it's going to do the exponent first, root 3 becomes squared, and then you multiply times 4 with no more exponent to take care of it.
So you do basically 4 times square root of 2 base 16, right?
Well, once you square it, yeah, 4 becomes 16, and root 3 becomes, no, root 3 squared is
3.
3.
So then that would just be times that by 3.
Yep.
And then be,
Parentheses around that one too.
and that would be 30 plus 18 equals 48.
Mm-hmm.
And then that one we do, that'd be, 36. And 6 times, right, times 6. 6, and then times that by 6, and 180 and 36. And
216.
Right, 216. And do you just add those together?
Close. But here's the problem. This is dangerous. because what you're doing is you've lost the formula. This is just an expression, but what you're really getting at here is a squared plus b squared equals c squared, right? So then you do all this stuff, and you end up with a squared is 48 plus b squared is 216, and that equals what?
C squared.
C squared, right? Because if you just do 48 plus 216, what are you going to get?
You just add them?
Mhm.
268.
264. Yeah. So you get 264. A lot of people will stop there and they'll just write the number on up here, but it's
And
not the
then
right
you
answer.
have to
Square root it,
square root it.
because it's 264 equals c squared.
Right, and then you have to break that down. Is there like a binding push for that?
For the square root symbol?
Yeah.
How
It's
do
the
you do
little
it
root symbol right
exactly?
there. It's above the x squared. It's use the second function for that.
264 and that.
No, that's squaring it. You want a square root.
You got to
You
put
have to do
the yellow
second
button.
square root.
But you can't put in decimal form.
Exactly. So for this one, you would want to break it down and simplify it. So the square root of 264, you need the factors. Usually start with the lowest prime number that you can.
Yeah.
Okay, that works.
44. 1, 2, and 2. Break that down to 3 and 2.
22 breaks down as well.
And that goes 11 and 2. And you're still with that 2. And that's 0 and that 3. And then you find pairs.
Yep.
So that breaks down to 2.
Any more pairs?
Yeah.
So what do?
You times them.
Recompose. Yep. With the root symbol, and then
That becomes. Oh, but you still got a 6 and 11. You times them together.
yep.
What's that?
So you've got 4 root, what was that, 3? 4 root 3, 6 root 6, and 2 root 66. Now, is that what she was doing in class when she was talking about simplifying the radicals, or is
Yes.
this something else?
It was that, and then it was just basically doing the other stuff with the 45, 45, 90. And
So converting from one side to another side,
yes.
that sort of thing? Okay. Do you remember any other problems with those that you were struggling with, where you were like, I don't know what to do, this doesn't make sense?
By heart, no.
No, okay.
That's when you're supposed to bring your stuff. So, what about ones with the fractions in the bottom? Were you good with those?
Thing by fractions.
Where you had to rationalize it because you couldn't leave the answer as a fraction. Then you leave the square root in the denominator.
Are you talking about having fractions within fractions, or just the radical symbols within fractions?
The radicals in the denominator.
So it wouldn't be things like 2 over 1/2, that kind of stuff? Okay.
No. Yeah, she had one.
I think you know what to do with that, right? Let me see. If I had 6 over root 3, what would you do? If that was your answer. I mean, that's perfect. That's exactly how you do it.
Oh, she knows how to do that?
Well, she did it pretty quickly, so I'm.
Okay, yeah, that means she knows.
Yeah.
Yeah, what about, so basically, it looks like the perimeter and area is just once she finds the sides, she'll be able to find the perimeter and area. They wanted to.
Yeah, the thing where people usually get tripped up with the perimeter is, do you know how to combine radicals and non-radicals? In other words, let's say that I gave you a triangle where you had, it was 3, 4 root 2, and this is not going to be correct, but 7 root 2. What would the perimeter of that triangle be?
Not sure.
Okay. How do you figure out the area? Figure out the area when you're looking at just a random shape. What are you supposed to do?
Well, when you're multiplying, then times what?
Well, that's not for perimeter, right? What's
For the
perimeter?
perimeter of the triangle.
Mm-hmm.
Can I see my thing?
You know perimeter. How you do perimeter of a triangle?
I'm not even asking you for formula. I'm just saying, like, how do you ever figure out perimeter? Like a square, a rectangle, a
Oh,
trapezoid?
you add the sides.
Yes, exactly. So what I'm asking is, do you know how to combine these sides? Like how to add them up?
I think you go like this. Right. That's, and then
No. So here's the thing. What you did is you wrote 7 root 2, right?
Mhm.
And then you wrote 4 root 2, but this magical root 2 has just appeared out of nowhere.
Oh,
Where'd it come from?
I thought this was supposed to be there.
Yeah, exactly. So the idea is that whenever you think something should be there, there should always be a reason. You always want to be okay, I'm creating a root 2 out of thin air because why? What rule told me I can do that, right?
Right.
So there is no rule that says, oh, that's a 3, so 3 is 3 root 2, just because it is. Doesn't happen. This is just plus 3. So how are you going to add those?
So I guess you do that one. And that one. That 11 plus 11 14.
No, hold on. Where'd the root 2's go? You did the same thing. Over here you created the root 2 and then you just made the 2 root 2's vanish into nowhere.
Oh no, I was getting there.
But where'd they go? Because you're adding 11 to 3, right?
Right. But then you go back to the root 2s and times
So you're going to
something.
have it be 14 root 2?
No, you 14 times 2.
So what's the answer?
Times 2 equals 20?
No, definitely not.
Okay.
So here's the thing. When did they multiply the root 2's?
Not sure.
They didn't. Because what's between the root 2 and the root 2?
Addition.
Addition, right? You're adding them. You're not multiplying them. You only do the operations that are there that you can see on
Wait,
paper.
so wouldn't that be 11 root 2 plus 3?
Good?
Oh, okay. Oh, I was thinking of multiplication like when we did it
Yep.
the other way.
Exactly.
Okay, 11 root 2 plus 3. Okay, so that's an addition. Okay, I got it. And then what do you do?
And then what's 11 root 2 plus 3?
Would that be 14 root 2?
Nope. What is 3 apples plus 4 oranges?
7.
7 what?
7 oranges.
So when you have 3 apples and 4 oranges, that gives you 7 oranges.
Wait, what?
Exactly. That's what I'm asking you. Imagine that I had 3 apples and 4 oranges on the table.
3 apples
And 4 oranges.
and 4 oranges. Oh, well then you just had 3 apples and 4 oranges separately.
Exactly. So when you have 11 root 2's, and this is 3 whats?
So you don't know.
No, you do know. What are these? These are 11 root 2's, right? Root 2, root 2, root 2, root 2, root 2. They're things. Root
Right.
2's are objects, right? So 11 root 2's and 3 whats? What are those?
Numbers.
Which number?
Not sure.
3 ones,
3 ones.
right? Because when you count, right? 1, 2, 3, you're counting ones. I have 1, 1, 2 ones, 3 ones, 4 ones, 5 ones. Does that make sense?
Yes.
Okay. So then here you're saying 11 root 2's and 3 ones. That's like saying 11 apples and 3 oranges. You can't do anything else because ones and
Oh,
root 2's
because
aren't
that's
the
the
same
final
thing.
answer because you can't add those two together.
Exactly. That's it. You're done. Now, if you had 7 root 2's and 4 root 2's, that's 7 apples and 4 apples. So you
Well,
can
so
combine
if you're
those
saying
together.
if those were, if that had a 3 and root 2, if there was like
Yes.
that, then you could add.
Then
like
you
that.
have 11 apples, 7 apples, 4 apples, and 3 apples. You just have a whole bunch of apples, so you can count them up and you're totally fine.
Okay, and then you'd have the root 2 at the end of that.
Yes, because that's what you have. Just like you would have apples at the end of counting up your apples, like you would still have root 2's when you're done counting your root 2's. So you still end up with the same thing regardless. But when you have this, you can't combine them.
Right.
So what if you had 11 root 2 plus 3 root 4, plus 3 root 5?
5?
Mm-hmm.
So there's a way to add it, right?
That's what I'm asking. Is there or isn't there?
No, maybe.
Nope, there's not, because these are,
root 2's.
and these are.
Root 5's.
They're different kinds of fruit again. You can't put them together. There's no way to do it.
Oh, so you're saying when they're opposites, you can't put them together, only when it's the same.
Only when it's the same radical.
Right.
So if it's 6 root 2 and 3 root 2, then it's
9 root 2.
9 root 2. When it's 6 root 2 and 9 root 3,
You can't.
it's 6 root 2 and 9 root 3. You're done.
Yeah.
That's it. Now, here's the funny one. What if I gave you 3 root 2 plus 5 root 18.
Maybe.
Okay.
Because that's an even number, and that can go into that. So maybe when you break that down.
Okay. So what do you get? Give it a shot.
That's 9 and 2. That's 3 and 2, and then maybe you can times that by that. You get 15 and 2 plus 3 and 2 is 2. Maybe?
Yes.
Okay.
Because what you had is you had root 18s and root 2s, and this is still not, you can't just combine these because they're different, but you can turn root 18s into root 2s by pulling out the 9, which becomes a 3.
Right.
Good. So it's like, in other words, like you can do anything that you want to as long as you have like a series of steps and a series of reasons for like, okay, I'm doing this because of this rule and this because of this rule.
Like proofs.
Yes. That's exactly what it is.
Mm-hmm.
I keep forgetting she's in geometry. Like that's what they start with.
Yeah.
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 So as long as you have a reason for it, it's fine. But this, yeah, once you get to that point, you're finished.
It's
Stop.
making sense.
Yeah, it should. Because that's the whole point of it. The whole point is to have a series of like of ideas that make sense and help you solve problems. And when they do, then they do.
Mm-hmm.
So those should work. Okay. So that's the hardest thing for the perimeter. Now the area. How do you feel about area? What's the what kinds of things are they asking you for that?
Don't remember.
How much time we got?
About like 25 minutes.
That much time? Oh my gosh. Okay. And it doesn't help that you can bring this stuff. Do you think it's home? Your materials?
Well, the nice thing about like having like a list of stuff is that you can condense it and you can get through like a whole laundry list of stuff like in a very short amount of time.
Okay.
Well, I just got through that. That makes sense.
Yeah, I know. I can tell that it seems to be clicking in your head. Yeah. He's
Which area?
great, right?
What's that?
I said he's great, right?
Oh.
The analogies with the apples and oranges. They
Yeah,
said,
yeah.
wait, you said apples and oranges, not
Yeah,
apples and
yeah.
apples. I was like, oh, whoops.
Yeah. Yep. So you're saying, so what kind of area problems did they have with this though? You gotta try to remember. So.
Because you know the area formula?
That's why I said it's in mine.
No, without the
Yeah,
chart.
Yeah, without triangles. So how do you find the areas of triangles?
Areas of triangles.
Right.
Like I would just write A equals blah. What's the blah?
Is it? Wait, this is not perimeter. This is area. I was thinking about pi.
Nope, no, there's no pi. Pi's are only for circles.
I don't remember.
Okay, here's how you're going to remember it. What shape is this?
It's a rectangle.
Exactly, right? What's the area formula for a rectangle?
1 times width.
That's right.
Oh, it's half. It's 1 times width times 0.5.
Good, why?
Because half of it.
Why?
Because half, and then makes another half, and then got a triangle.
Well, that's true, but here's the thing. If I cut a rectangle in half, what kind of a triangle do I make?
Is it 45, 90?
That would be a square. This is a rectangle.
Oh, 90 degrees.
It's a right triangle,
Right
right?
triangle.
So that works for a right triangle, but what about a non-right triangle? What about one that looks like that? It's no longer half a rectangle.
Right.
So does it have the same area formula?
No.
Yes, it does.
It does?
Yep, here's how. So I have my rectangle, right? And I know that the area is the length times the width. So here's the width, and here's the length. Good?
Mm-hmm.
All right. So what I want you to do, you're going to pick a random point along one side, okay? And you're going to draw a line from the corner of the rectangle down to that point. It doesn't really matter where it is because it's a generalized thing. It will apply anywhere. Pretend this is a block of wood. I'm going to cut off this triangle from one end, and I'm going to move it down here.
Right.
Okay? And I'll reattach it.
Oh, parallelogram.
Exactly. It's become a parallelogram. Has the area changed?
No.
No, because I have the same amount of wood, right?
Right.
Nothing's changed at all. But here's the thing. It's no longer the side times the side, right?
Mm-hmm.
Because this side is longer.
Base times height?
It's base times height.
Right.
It's the perpendicular height to the base. It's this thing.
Which would be that.
And this, exactly. So now it's area equals base times height. Now if I draw a line from one corner of a parallelogram to the opposite corner of the parallelogram, I got a random triangle. In other words, not just a right triangle, but any triangle. And now it's going to be area equals
Base times height?
1/2.
1/2
base
times
height.
base times
Exactly. You cut off half the parallelogram and you've got your shape.
So
And
that's
your
always gonna be the
0.5.
same.
That's always going to be, for any triangle that you do, it's always 1/2 base times height. Now, here's the hard question. Which side is the base?
I think that's the base and that side.
Nope. It can be. It doesn't have to be, though. The base can be any side that you want it to be.
So it could be this,
Yes.
this side too.
So if that's the base, where's the height?
There.
Nope. Because that's the height from this base.
Oh.
Every base has its own height. So you can use whichever base you want, but you have to use its own height. You can't just like switch it around and say like I'm going to use this height from this triangle over here in this base. So what I need to do is I need to pretend, okay, here's my new triangle, right? So I'm going to make this my base.
Right.
Where's the height of that triangle?
Right here.
Nope. Because if you had a building, right,
Mm-hmm.
that was built on the ground, would you measure diagonally up it to figure out how tall the building was?
No.
How would you measure how tall the building was if this was the ground?
Wait, this is the ground and this is the building?
This is the ground and this is the building. How would you figure out how tall the building was?
From here to here.
Well, this is the ground, right?
Mm-hmm.
And here's a building. It's slanted. It's Leaning Tower of Pisa.
Right.
Okay? So you got the building. You want to figure out how tall it is above the ground. How are you going to measure that?
Not sure.
Well, you're going to go to the highest point of the building, right? And you're going to drop a really long ruler down to the ground.
And just made another triangle.
Mm-hmm. And it'll tell you the height of the object, right? So what you're going to do, once you've picked your base, you're going to go to the furthest point in the triangle that you can,
Mm-hmm.
and you're going to drop a perpendicular, which means that when you go to the base or you extend the base,
Oh, that's what they mean by saying perpendicular to the base. Oh.
exactly, there's going to be a right angle right here,
Mm-hmm.
and that's going to be your height.
I'm gonna start buzzing.
All right, so if what I'm going to do is I'm going to take, let's say that this is my, I'll just make this simple. Here's my triangle. If this is my base, then I'll extend it, and I'll drop a line perpendicularly to it,
And that would be
and that's the height of
Height.
the triangle. If
perpendicular
I
to the
turn
base.
it around, and this is the base, and I start at this point and drop a perpendicular, that's the height. And if I make that one the base, and I find the furthest point and drop a perpendicular from it to the extension of the base, that's going to be the height. So every base has its own height. Now here's the thing. If I pick the long base, which height have I picked?
Middle?
The small one, because this is the shortest of the three heights. If I pick the short base, which height do I have?
The second one.
Well, is this one longer or shorter than that one?
Well, that one's longer and that one's shorter.
So the shorter base gets the taller height, and the longer base gets the shorter height.
So it's
Because
opposite.
as the base goes up, the height goes down, so that the base times the height is always what?
Half of that.
The same thing.
Oh.
Because I don't want the area to change. If I turn the paper around, how much bigger is the triangle?
And like a little bit smaller, or is it exactly the same?
So here's the triangle. If I turn the paper, is the triangle getting bigger or smaller? Think carefully about this. I'm turning the paper on the table. Is the triangle getting bigger or smaller?
Smaller.
It is?
Bigger?
It still is.
How many times would I have to turn the paper for the triangle to be the size of the table?
Is that a trick question?
No? I'm asking you how long would I have to be spinning this paper around on the table before the triangle grew to be the size of the table?
Why didn't you have to extend it and just get bigger out of nowhere?
Yes. Okay, so this one isn't working. It doesn't matter how long I turn this paper. That triangle is not going to change.
Okay.
That's the whole point. If I turn the paper to pick it so that this is the base, and if I turn it so that this is the base, the triangle didn't get any bigger.
Right.
So the area didn't change.
But
So
the height changed.
to match the base. So in other words, when the base shrunk, the height grew, so that the base times the height always stayed the same number.
Oh.
In other words, no matter what I do, this is a transfer. You were talking about transformations before, right?
Yes.
This is a transformation called rotation. When I
Right.
rotate a geometric object, it doesn't change in size. It stays exactly the same. So if you're going to use a different side for the base, the height's going to change to match it so that the proportion stays exactly the same. It's never going to change away from that.
Okay.
Good?
Yep.
Okay. So when you're looking at it, which base are you going to pick when you're trying to solve an area problem? Because you have 3 choices.
The shortest one?
Whichever one makes your life easiest. So in other words, if you are looking at a problem and one of the, like let's say that I'm looking at a triangle that looks like this.
Mm-hmm. Base times height times 1/2. That.
Which side will you pick for the base?
I probably pick this one for the base and that one for the height.
Or you could pick this one for the base and that one for the height. But I won't pick this for the base and that for the height.
Because that's complicated.
Because I'm adding another line, I'm adding another thing to figure out, right? I'm going to have to figure
Which
out
is more work.
more triangles. Exactly. So with a right triangle, you're usually going to pick the 2 sides that have a right angle between them to be the base and the height, because then they're already taken care of. The base already has a right angle. With the height, you don't have to draw any new lines, you don't have to create anything extra. So you just stop here. If I was going to be dealing with a, let me think about this, what's the other one? So if I'm dealing with a 45, 45, 90, and I want to know the area, which side's my base?
Oh, 45, 45, 90? So there's 2 legs and you're trying to find the hypotenuse like that?
No, I'm trying to find the area.
Oh, you're trying to find the area.
So which side will I use for my base?
This one?
So you're going to use a side for the base that requires you to draw another line going through the
Oh,
triangle.
no,
to
no,
get the
no,
height.
that one.
Exactly. You're going to use this one because this one's already given, and that one would be
The height.
the height. Exactly. So let's say that I gave you a 45, 45, 90 triangle, right? And I gave you a height, or a hypotenuse of 7 square root of 2.
Yeah.
What is the area